First of all, I would like to thank everybody for joining this special month on singularities and k-stability at the University of Utah. Unluckily, we have to do this via Zoom. Hopefully, the next meeting will be in person. It's great to see so many people joining us, and I'd like to thank all of the speakers that have agreed to talk. The plan is to have these 2 mini courses running simultaneously in the first 2 weeks on Monday, Tuesday, Thursday, and Friday. Almost all the talks will be at noon, except for Show's talk will be, I believe, at 4 p.m. Utah Mountain Standard Time because of the time difference with Japan. And then in the last 2 weeks, we will have a talk every day. I think all of them are scheduled right now at noon, so there should be no time surprises. But again, all times are Mountain Standard Time. When you click the Google Calendar link, it might translate the time to your time zone, so be aware of that. We are going to try and record the lectures and post them on a Zoom link, which will be available sometime later today once Carl figures out the details. So if you can't make it to one of the lectures, you should be able to make it up if you're interested. We are also planning to have some social gatherings. I think they're planned on Tuesdays and Thursdays, held via GatherTown. We don't have the link up yet, but it should be up later today. And again, it will be announced tomorrow during the talk, and there will be a link on the webpage. Also, we're planning on having a poster session. The poster session is on June 3rd, which is in the 3rd week of talks. It's typically aimed at graduate students or postdocs. If you are interested in giving one of these, in presenting a poster, fill out the form on the webpage. Please do that by the end of the 2nd week. And then we'll contact you and try and get it all organized. So I think that is the list of all the important announcements that I need to make. So yes, I don't think I'm forgetting anything. Just make sure that you're muted. If you have questions, feel free to ask them on the chat and we'll try to troubleshoot them. Of course, if there's something that's really important for everybody to, if Bhargav makes an unlikely terrible typo, maybe you do want to bring it to everybody's attention. Or if you put it in the chat, we'll try to bring it to everybody's attention. So maybe without further ado, let me introduce Bhargav Bhatt, who's going to tell us about mixed characteristic vanishing and applications. Thank you, Bhargav.
Great. Thanks a lot for this invitation. It's fun to be here. Let me maybe start sharing my screen. Okay. Yeah, so this is the first talk of a series of 4 talks on mixed characteristic vanishing theorems and applications. The first 2 talks, which are the ones I'm giving, are going to be on Kodaira on some versions of Kodaira vanishing in mixed characteristic, and then in the 3rd and 4th talks, Sho and Jakob will talk about how to use these vanishing theorems to prove results in the MMP in dimension 3 in mixed characteristic. Okay, so yeah, as I said, my plan is to talk about these vanishing theorems in mixed characteristic, and so these are relatively recent results. They're from last year. The results somehow crucially rely on a lot of modern advances in p-adic Hodge theory, as well as a little bit about the theory of perverse sheaves in characteristic 0. And so there's some background that goes into it. And so my plan for the first 2 talks was to explain how the arguments in mixed characteristic work in an easier setting. So try and first do the arguments in characteristic P by using some of the ideas that we'll later generalize. And then once we have that in the 2nd talk, I'll explain what actually happens in mixed characteristic. But my sort of the thing I want to emphasize in these talks is that the Kodaira vanishing theorem in any of the incarnations that I'm going to talk about, to me at least, that's kind of the crucial vanishing comes from topology, and then you need some machinery involving Hodge theory of some sort to go from topology into algebra. And so I would like to sort of make that clear in sort of 2 examples today, namely in characteristic 0 and in characteristic P. And then the next talk will be on mixed characteristic. Okay, so that's the plan. And yeah, as Christopher said, if I make a typo, or if you're confused about something that just looks wrong, or whatever, just feel free to ask questions. I think the talk goes much better if there's more interaction. Okay, so let me begin by recalling Kodaira vanishing just in pure 6-0 in the most classical form. So I'll work over the complex numbers. And I'll just, let me remind you what the theorem is. So say X over C is a smooth projective variety. L is an ample line bundle. And I guess the dimension of my variety is going to be D, actually. So let me put that over here. And then the Kodaira vanishing theorem says that the cohomology groups of the negative powers of L vanish in degrees less than the dimension. So I'll write it like so. H less than D, so cohomology in degrees less than equal to D of L inverse vanishes. Okay, and so I'll make some comments on this result in a bit. I'll explain why it's useful and what kind of more concrete statements it buys you. But maybe I want to actually begin by sketching a proof to emphasize the proof in a simple case, so to emphasize sort of what the input is from Hodge theory or from topology. So proof sketch. And so let me make a simplifying assumption, which is let me assume that L is very ample. You can reduce to this case by the cyclic covering trick, but I'll just assume L is very ample to start with. So and so what this buys for me is that I can find an ample divisor in the linear system defined by H, which is which is non-zero, which is smooth. Sorry, ample divisor which is smooth by Bertini. And so I will use this ample divisor and sort of Hodge theory on both X and on the ample divisor to try and explain where the vanishing comes from. And so in this setup, what does Hodge theory tell me? So, well, it tells you lots of things, but the relevant feature for me is the following. So it tells me that the nth singular cohomology group of X with coefficients in C has a decomposition. Hi into I, the direct sum over I plus J equals N of hi of X, omega J of X. So it's the cohomology of X with coefficients in the sheaf of J forms on X. And then similarly for H. So maybe I just write it. Because H is smooth. Oops. I apologize. Okay, and so we have an obvious kind of restriction map that goes from here to here. And the restriction map preserves the Hodge decomposition. So it sort of preserves the sum ends of my Hodge decomposition. And this line bundle L, the relation between L and H is that L is O of H, or equivalently, L inverse is O of minus H. Right? So H was an ample divisor in the linear system defined by L. And so O of minus H is the kernel of the map from OX to OH. And that shows up as the J equals 0 sum end of this map, of the restriction map. And so if I just restrict to the J equals 0 sum end, the map I get is exactly the map from OX to OH. And so I'm trying to say something about the kernel of that map. And so it's enough to understand something about the kernel of this ginormous direct sum instead. And so let's try and do that. So let's try and analyze the restriction map. And there's this general sort of long exact sequence in topology. So let me recall what it looks like. It's the exact sequence for compactly supported cohomology. So I have the cohomology of X in the middle. It maps via restriction to the cohomology of H. When I don't sort of specify what kind of cohomology, I mean singular cohomology. And what goes in over here is the compactly supported cohomology of the open variety, which is X minus H. And so we are trying to prove, well, we're going to try to prove that this map is an isomorphism in low degrees, so in degrees less than the dimension, which means we're going to try and prove that this guy is equal to 0 in degrees less than the dimension. So suffices to show that the compactly supported cohomology of x minus h is equal to 0. Maybe I'll just keep the same notation. So h less than d of x minus h is equal to 0. And so now we've converted what we want, which was a question about sort of the cohomology of this coherent sheaf on x, into something about the topology of the complement of h and x. And so, okay, so far so good. I guess I used the smoothness of h to get the Hodge composition already, but now I'm going to use the smoothness of x again to argue that since x minus h is smooth by Poincare duality, the compactly supported cohomology of any variety is dual to the usual cohomology of that variety, provided the variety is smooth. So to understand the compactly supported cohomology in low degrees of x minus h, we need to understand the usual cohomology in high degrees of x minus h. And so this theorem over here is equivalent to proving that h bigger than d of x, or sorry, of x minus h is actually equal to 0. Okay, and now we're in good shape. So there's this classical theorem, which is called Vanishing, which says exactly the statement. So in the analytic category, it's an older result. It's Andreotti-Frankel vanishing. What they prove is that whenever you have an affine variety, a complex affine variety of dimension d, it actually has the homotopy type of a d-dimensional CW complex rather than a 2D dimensional CW complex. So kind of the cohomology shrinks by half. And that tells you in particular, that applies over here because H was an ample divisor. So the complement, well, so the complement is actually affine. And so you can apply Artin or Andreotti-Frankel vanishing to get the conclusion that you want. And so, okay, that was a very kind of rough sketch of the proof. And it's not super important for what follows, but I want to emphasize that there are kind of two inputs that are going into it. One is this kind of purely topological vanishing, which is the Artin vanishing theorem, which is something about what x minus h looks like as a topological space. And the other is Hodge theory, which is sort of allowing me to translate stuff I know on this side, on the topological side, to conclusions on the coherent side. And the same kind of process is going to repeat itself in characteristic P and in mixed characteristic. And so this is kind of the take-home message for these talks. Okay, are there any questions about what I've said so far? So far I just recalled what Kodaira vanishing is and very roughly told you how to prove it using topology. Okay, so let me make some remarks about this result. So how does one go about using it? And this will be sort of elaborated upon in future talks when sort of fancier versions of this application will come up. But here's kind of a typical way one goes about using it. So if I fix x and L as above, so x is a smooth projective, L is ample, and D is a divisor, some divisor, then the claim is that H naught of x with coefficients in omega x of D tensor L mapping to H naught of D coefficients in omega D tensor L. So there's a restriction map on sheaves, which goes from omega x twisted up by the divisor to omega of the divisor. It's the residue map if you're thinking in terms of differential forms. And so I can twist it by L. And the claim is that that map is surjected. And the reason is very simple. If you just think about what the long exact sequence tells you, the next term in the long exact sequence will look like H1 of x with coefficients in something like omega x tensor L. And that's the object which is Serre dual to something that vanishes by Kodaira vanishing. So it's just a formal consequence of Kodaira vanishing plus Serre duality. But what it tells you is that if you have a bunch of sections of this sheaf on the divisor, you can lift them to sections on X. And this lifting process of sections to go from divisors to the ambient space will be very useful later in sort of making inductive arguments for proving that certain sheaves are globally generated, for example. And so maybe for people that haven't seen this before, an exercise is to show using this argument that if L is very ample, then omega x tensor the d plus first power of L is actually globally generated. It's sort of simple inductive argument. And sort of fancier versions of these are conjectured by Fujita, but this particular version is quite simple. So the thrust of the applications is, or at least some of the applications, is that you can do this lifting argument to go from divisors to global sections on X. The second thing I wanted to mention is that sort of in applications, you often want to relax the assumption that L is ample, because this assumption is not stable under certain operations like blowups. If you take a variety and you sort of take a blowup along a nice center, and you pull back the ample line bundle, it's not going to be ample anymore because it's sort of trivial along the curves in the fibers, but it still has sort of pretty good positivity properties. And so there are versions of Kodaira which account for this operation. And so there are versions with weaker positivity assumptions. And so the one that I want to mention is Kawamata-Vivek. So they say that you can actually take L to be any line bundle which is Neff and big. And so Neff and big has the property that it's stable under this blow up, pullback along blowups. And so it's a more useful version of this theorem in practical situations. So that's one version, and there are versions with weaker assumptions on L or with coefficients in sheaves of differential forms. And so I don't want to sort of get into the second one too much. It's the Kodaira Akizuki Nakano vanishing. But basically, if you sort of look at the proof that I sketched over here, I only used the j equals zero sum end to get a conclusion. And so you might wonder that for higher values of j, I'm still getting some conclusion out of this argument. And what is sort of the natural statement I get there? And that would lead you to Kodaira Akizuki Nakano vanishing. But as far as these talks are concerned, the relevant assumptions are, the relevant generalization is going to be the one in Kawamata-Vivek. And so we'll see later that some shadow of this statement is also true in mixed and positive characteristic. And then maybe finally, the third remark I want to make about this is that the statement literally taken, so it's a statement in pure algebraic geometry. It doesn't really make sense. I mean, it doesn't, there's no reason to restrict over the complex numbers. The statement makes sense over any field, but it's completely false if you're not over a field of characteristic zero. So if you're over a field of characteristic zero, you can immediately reduce to the complex numbers and you get the same conclusion. But away from characteristic zero, the statement is just false. So I'll say it this way: KV fails in characteristic P, even in dimension 2. So I think the first examples were written down by Raynaud. And by now, there's kind of a industry of people producing examples, counterexamples rather, to Kodaira vanishing. I think one of the simplest examples is in a paper by Lauritsen and Rao, where they explain that a principal homogeneous space for SL4 is a counterexample to Kodaira vanishing. And so there's no hope of having literally the same statement in characteristic P. And so then you might wonder, what is the point of this entire lecture series if the statement is just false? And so there are substitutes, and we're going to talk about some of these substitutes. So that's where we're going. Okay, so I want to switch to characteristic P now, and then eventually mixed characteristic. But maybe before I do that, are there any questions? Okay.
There was a question in the chat, and I also don't understand it.
Oh, sorry, I'm not looking at the chat. So can someone read the question? Or
sure. It says,
oh, sorry. By characteristic zero, we mean residue characteristic also zero, right? So sorry, when I guess I should have specified this at the start. So when I say characteristic zero, I say a scheme is characteristic zero if it's a Q scheme. So all residue fields are characteristic zero. And I say the scheme is characteristic P if it's a scheme over FP. So in particular, all residue fields are characteristic P. And rings like Z mod P to the N for N bigger than or equal to 1 have no characteristic. And rings like ZP, the p-adic integers, which will come up later, is going to be mixed characteristic. Is that okay? Right. So, okay, let's talk about Kodaira vanishing in Kersic P now. So the setup is going to be similar. So maybe my ground field K is going to be a perfect field of Kersic P. You can take it to be a finite field if you like. X over K is going to be a proper variety. I will not make a smoothness assumptions on my variety yet. I will when I have to. Of dimension D. And L is going to be a line bundle on X. And again, when I formulate proper statements, I will make more positivity assumptions on L. And so I want to first talk about a version of this Kodaira vanishing theorem in Kersic P, which is due to Delin and Luzie, which is incredibly nice looking. It looks very parallel to what happens in Kersic 0. And so it's the following statement. So I will call this Delin and Luzie Kodaira vanishing. So I want to talk a little bit about the history of this theorem, but maybe I write the theorem first and then talk about its history. So what they proved is that if you assume that X is smooth, and L is ample, so the same kind of assumptions that we had in Kersic 0, but you also assume, crucially, that X lifts to W2 of K. So what this means is that if so there has to be a flat lift of your variety with coefficients in something that lives over Z mod P squared rather than over Z mod P. So if you're imagining your variety came by reducing mod P, a variety that lived in Kersic 0, then this will be automatically satisfied. But there are examples of perfectly nice smooth projected varieties in Kersic P that do not satisfy this condition. So it is a non-trivial constraint. And then in that case, what they prove is the exact same statement. So the cohomology of negative powers of the ample line bundle vanishes in degrees less than the dimension. And so I wanted to talk a little bit about where the statement came from, and then maybe what some issues with using it are. So this history of the statement is kind of interesting. So my understanding is that there was a paper by Faltings where he first proves something called the Hodge-Tate decomposition, which is the p-adic analog of the Hodge decomposition. And he makes a remark in this paper that this gives a purely sort of arithmetic or algebraic proof of the Hodge to de Rham degeneration, which until then had no algebraic proof. And then Kato observes that if you take Faltings' proof and you sort of try to do things integrally, so p-adic Hodge theory is a setting in which you can either invert P or you can work sort of integrally and then eventually go mod P. So Kato observes that in the framework of p-adic Hodge theory that he was thinking in, the same arguments would actually give you Hodge to de Rham degeneration integrally, meaning over ZP. And so Kato essentially proves the same statement over here, except instead of lifting to W2, he needs to lift all the way to W, which for practical applications doesn't make much of a difference. And then Delin and Luzie say in their paper that they were trying to understand what Kato and then Fontaine-Messing also did. And they came up with this argument, which is now sort of purely a Kersic P argument, which doesn't really use that much p-adic Hodge theory, except maybe in this kind of slight shadow of having a lift to Z mod P squared. But the argument is somewhat purely in algebraic geometry in Kersic P. The sort of non-formal input to their argument is something called the Cartier isomorphism. Okay, so right, so that was something about where this theorem came from. Maybe one thing I should say is that, right, so first of all, this Delin and Luzie version of Kodaira vanishing is very useful if you want to prove stuff in Kersic 0. So for example, this implies Kodaira vanishing in Kersic 0. So the idea is this kind of general spreading out machinery where if you start off with something that lives in Kersic 0, like over the complex numbers, it's defined by finitely many equations, and those finitely many equations have coefficients in some finitely generated Z algebra. And so you can work over that Z algebra and start reducing modulo various primes to get to Kersic P, invoke Kodaira vanishing there, and then eventually try to go back. And so it's some standard sequence of maneuvers, which allows you to go from this statement that happens in Kersic P to something that happens entirely in Kersic 0. The other remark is that this theorem is actually not that useful if you want to work entirely in Q6P to start with. So if you're interested in just doing algebraic geometry in Q6P, you might not be in a situation where x lifts to z mod p squared, for example, and then you can't apply this theorem. And even if you were in that situation, you might do some geometric maneuvers to it, like blowups. And if you don't choose your blowups very carefully, the blowup will lose this property of being liftable to z mod p squared. And so it's not an assumption which is very robust under geometric operations. And so that makes it slightly harder to use. And somewhat related to this is the following, which is we don't know an analog of Kawamata-Vivek in this setting. So it's unknown, I believe, if L being nef and big is enough. There's the argument in Q60 that goes from the ample case to the nef and big case relies on resolution of singularities. And so you can't run that argument over here because we don't have resolutions. And so this is not really the direction I want to go in this talk or in the next talk, but I wanted to mention it as like an example, as an instance of Kodaira vanishing that exists in Q6P, and it's really a vanishing statement on the nose. But this is the one that's not so useful. Instead, I want to talk about a different set of ideas, which turns out to maybe be more useful in some other applications. So I think the idea for what I'm about to talk about goes back to work of Hochster-Hunnecke and Karen Smith in commutative algebra. And what they were observing is that there were sort of analogous vanishings in local commutative algebra and local algebra. So instead of coherent cohomology of projective varieties, you think about local cohomology of commutative rings. And there, again, the statement was not quite true on the nose, as you might expect from Q60. But you could always find a finite extension of your ring where the cohomology classes became 0. So somehow the vanishing statement is true up to passing to finite covers, was the result that came out of thinking along those lines. And so the natural kind of culmination of that sequence of ideas is the following result, which I want to mostly spend the rest of this talk on. So this is Kodaira vanishing in Q6P. Oh, this is the version of Kodaira vanishing in Q6P that I want to talk about. And so this is Hochster-Hunnecke, mostly in the early 90s. And the sort of analog of Kawamata-Vivek in this setting was in my thesis maybe 10 years ago. And so here's the statement. So I'm still in the above setup. So I have my perfect field, I have my proper variety, and I have my line bundle. And I'm going to assume that the line bundle is semi-ample and big. So semi-ample means some power is globally generated. And so therefore, this power defines a morphism to projective space. And then bigness means that this morphism is birational onto its image, at least for a sufficiently large power. So a typical example is you take an ample line bundle on a variety, and then you pull it back to something that's generically finite over that variety. And that pullback will be semi-ample and big. So like a pullback to a blowup. And then the theorem in this case says the following. So there exists a finite cover. So maybe I'll be precise about it. So finite surjective map pi from y to x such that pi upper star, so pull back along pi, kills the following groups. Or I think I was told I should not say the word kills, so annihilates. Following. So first it annihilates positive powers of the cohomology of positive powers of L. It also annihilates the cohomology of negative powers of L in degrees less than the dimension. So that's the analog of Kodaira. And it also annihilates the cohomology of the structure sheaf in positive degrees. So this is something that doesn't really have an analog in Q60. And so maybe I emphasize this. So this is analog of Kodaira vanishing, whereas these two over here, they're specific to Kersig P. And so that's the statement that I want to focus on. And later on in mixed characteristic, we'll have a very similar statement that I'll talk about next time. And so again, I want to emphasize something about what the statement is saying. So it is not saying that the cohomology on Y with coefficients in the pullback of L inverse is 0 in those degrees, right? It's only saying that if you start out with classes on X that shouldn't exist, like classes in here, then they will always die when you pull them back to Y. But it could very well be the case that on Y, there are new classes that are produced that shouldn't be there. And so then you have to sort of, if you want to kill the group entirely, you have to somehow pass to the limit and formulate a statement there. And I'll come to that later in this talk. But so that's the statement. And I want to make some remarks on it. But maybe before I let it scroll off the page, are there questions?
I have a question. So the theorem says that, for example, B pi upper star annihilates that, but it is not true that H less than D of Y, the pullback of L inverse vanishes, right?
Correct. That's not true. And I believe there are examples where that cannot be true. So it's always non-zero for any finite cover. Okay, so maybe, yeah, remarks. So first remark is that all parts of the theorem are false in Kersig 0. So if you just take the statement as written, it parses certainly in Kersig 0. It's a mathematical statement that you can contemplate. And the assertion is that all the statements you get this way are just false. And the reason is very simple. The reason is that in Kersig 0, if you have, let's say, a normal variety, and you pull back along a finite map, that's never going to kill any coherent cohomology because you can always trace back down. And the composition is multiplication by the degree of the map, which is non-zero. So the pullbacks on coherent cohomology, when the base is normal, are always injective. And so this maneuver of pulling back to a finite cover accomplishes nothing in Kersig 0. And you can give examples just to see that all three of them will be non-zero. And so this is really something that's specific to Kersig P, and it's exploiting the fact that the covers you're going to pull back along have degrees that are divisible by P. And so this kind of trace argument of tracing back down doesn't produce an obstruction. The other remark is that I assumed L is semi-ample in big. In analogy with Kawamata and Vivek, the natural assumption would have been Neff in big rather than semi-ample in big. But that we don't know yet. So at least I don't. So Neff in big case of part B is open. And for A, it's false. Okay. But semi-ample and big seems to be good enough for many geometric applications, at least the ones that concern line bundles that are positive in the sense that they're sort of pulled back from something ample along the generically finite map. I should also say a little bit about the history. So basically, the case for L ample. So Hochster-Hoenicke handled the L ample case, and then my thesis was about extending it to the semi-ample and big case. I'll just say it that way. Okay. Okay, and then maybe the final remark I want to make, and this is also where I'm going to use this as an opportunity to segue into the proof, is that so in Kersig P, if you search for what are some natural finite covers you can use to do things, there's one that stares you in the face, which is the Frobenius. So Frobenius on any variety is a finite morphism from the variety to itself. And it has certain features which we can exploit. And so you can ask if Frobenius itself does the job for killing, for annihilating these cohomology groups. And it turns out it's not enough for 2 and 3, or for B and C. It is enough for A, as I'll explain. So just using Frobenius is not enough. or 2 or 3. And it is really easy using Frobenius, as I'm about to explain. Okay, so my plan for this talk, for the rest of today's talk, and at least for the next 15 or 20 minutes, is to explain a proof of this theorem in a way that sort of will later be able to adapt to mixed characteristic. So the statement of mixed characteristic is going to be very similar. And I want to explain a proof of this in a way that is maybe not the most intuitive if you've already seen these statements before. Like the standard proofs of these are maybe slightly different than the one I'm presenting, but it will be very useful in sort of mimicking later. Okay. So let me do sketch of proof. So again, I want to explain why, given my variety X and the semi-ample and big line bundle L, I can kill the cohomology of positive powers of L. And so let me simplify my life and just assume L is ample for now. I can explain later what people, if people are interested in what you need to do to extend to the semi-ample and big case. So kind of the key trick, key observation for part A, and for a lot of this stuff, is that Frobenius pullback of L is L to the P. Where Frob is the Frobenius map. So this is the map that's the identity on underlying topological spaces and is given by the pth power on functions. And because it's given by the pth power on functions, if you just think in terms of what the cocycle representing L looks like under the Frobenius, you immediately see that its Frobenius pullback is going to be its pth power. And so what this means is that if I do Frob to the n upper star of L, I'm going to get L to the P to the n. And now we are in good shape because Ser vanishing, sort of the easy statement from Hartshorne will tell you that the cohomology in positive degrees of X with coefficients in Frob to the n upper star of L is equal to 0 for n sufficiently large. Right? If you take an ample line bundle and take huge powers of it, those powers are not going to have any higher cohomology. And so those huge powers can be thought of as pullbacks along Frobenius to the n. And so therefore, for part A, so for killing the cohomology of positive powers, pi y to the x, this finite cover can be taken to be the Frobenius. Okay, so this was very simple, right? You don't have to do much. You just invoke Ser vanishing and then reinterpret what it's telling you. And so now let's see what happens if you try to mimic something, mimic this argument in the second case. So the second case was when you want to deal with negative powers of L. And so again, if you want to deal with negative powers of L, you try to use the same argument. You will have L to the -1 will be replaced by L to the minus P to the n if you pull back along Frobenius to the P to the n. But now if you want to invoke Ser vanishing, you need positive powers of L. So it's tempting to use duality. And so let's try and see what it tells you and see what the problem is. So by Ser duality, the cohomology, let's say in degrees less than d of X with coefficients in L inverse, the object we're trying to kill, it's going to be dual to the cohomology in positive degrees of X with coefficients in something that looks like so. Okay, so this guy over here is the dualizing complex. And this is kind of the crucial point. So usual Ser duality for coherent sheaves works really well in Cohen-Macaulay varieties. If your variety is Cohen-Macaulay, then the dualizing complex is a dualizing sheaf. It's an actual sheaf. There's no sort of fancy derived stuff going on. And you just get a very simple looking statement. But in general, your variety might not be Cohen-Macaulay. And so the dualizing complex is now going to be a genuine complex. And so that this complex can have cohomology groups and cohomology sheaves in positive degrees. And so those cohomology sheaves in positive degrees, when you tensor with L, they could have an H0, and that H0 is going to contribute over here. And that is a contribution, since it's coming from an H0, you're never going to be able to kill it by going to just sort of naively pulling back along the Frobenius. And so what you need is some kind of statement that says that every variety is Cohen-Macaulay. Now that's obviously not true, right? There are non-Cohen-Macaulay varieties out there. But we're only trying to prove something about the collection of all finite covers of my variety. You're just trying to prove that there is a single finite cover where these classes can be killed. And so what you need is not quite the statement that every variety is Cohen-Macaulay, but rather the statement that sort of the collection of all finite covers of X looks as though it was a collection of Cohen-Macaulay varieties. And that's exactly the statement that Hoxha-Hoenicke actually proved. So, and so that's what I want to recall now. And so maybe I should first say, so because of this, what I just wrote over here, the previous argument for vanishing works if X is Cohen-Macaulay. And so Cohen-Macaulay means that omega X bullet is actually a sheaf. Because then you can just repeat literally the same argument I wrote, and you take Serre vanishing not with coefficients in O, but rather with coefficients in this sheaf. But in general, we need the following, which is kind of the key theorem. And so I'll call this theorem HH for Hoxha-Hoenicke. And so what they proved is the following. So for any X is above, so for any proper variety over a perfect field, say, there exists a finite cover, pi from Y to X. So you want to say that Y is Cohen-Macaulay. If that was true, then you'd be done. But that's actually not true. So again, there are counterexamples to that. But as far as the map is concerned, it looks as though it was Cohen-Macaulay. And so the precise statement is there exists a finite cover pi from Y to X such that the trace map from the dualizing complex on Y to the dualizing complex on X factors over H naught. Which is the dualizing sheaf. And so as far as Y is concerned, X acts as though it was Cohen-Macaulay because the trace map is factoring through a sheaf rather than going through this kind of genuine complex. And so this is a non-trivial theorem. We'll sketch a proof of this maybe in my next talk. But if you believe this theorem, then it's very easy to see that the following will do the job. So for any Y, or maybe I shouldn't call this map pi, because pi is the map I'm trying to find. So let me call this F over star. So if I find this kind of Cohen-Macaulayfication or this kind of weak Cohen-Macaulayfication of X as above, the composition of this map with a high enough Frobenius will solve the problem. So if I do Frob to the n over here, and then I do F to go down to X, it solves the problem. Okay, so basically you have to repeat the argument that I gave in part A to see why this is enough using this factorization property. And okay, I'm sorry this got a little technical, but I want to emphasize the key point, which is this Hoxha-Hoenicke theorem that says that the collection of all finite covers behaves as though it was Cohen-Macaulay in this sense, that the dualizing complexes, the maps between them factor through sheaves. Okay, are there questions so far?
I have a question, but it may be like maybe naive. Then this condition factoring through H0 be related to saying that the relative dualizing complex is a sheaf?
I'm not saying that the relative dualizing complex is a sheaf. I'm just saying that the map on dualizing sheaves is going to be 0 on everything except the bottom cohomology sheaf. Right, so the cohomology sheaf upstairs could have stuff in H0 and H1. The cohomology sheaf downstairs could have stuff in H0 and H1. But the map on H1s is 0, so it's factoring through an H naught.
Thank you.
Mm-hmm. Yeah, so, okay. So let me maybe give you a reformulation of this, which points in the direction of what we need to do later. So if you want to mimic these kind of arguments and mixed characteristic, one lesson is that you're not allowed to talk about the Frobenius. If you're working in mixed characteristic, Frobenius is not available. So you need to come up with statements that are formulated in a way that doesn't refer to the Frobenius. And one way to reformulate this Hochster-Hunicke theorem is the following. So say x plus to x is the absolute integral closure. So I'll say what this means. So what this means is that you take the normalization of x in an algebraic closure of its fraction field. So if you like, it's the inverse limit over all finite covers of that finite cover. So it's some ginormous object. It's a bookkeeping device to talk about the collection of all these finite covers as a single object. It's very non-Noetherian, but we have learned in the last 10 years not to be scared of that. And then in this case, what the Hochster-Hunicke theorem is really saying is that the push forward of the structure sheaf from this huge kind of profinite cover is a Cohen-Macaulay sheaf. So it satisfies the same kind of vanishings that a Cohen-Macaulay module would satisfy. So if you know what a Cohen-Macaulay module is, you know that one way to characterize it is in terms of certain local cohomology groups vanishing. And the assertion I'm making over here is that those exact same vanishings will be satisfied for the sheaf. So for example, maybe I just tell you the most important one. So one vanishing that's satisfied is that if you look at the local cohomology at a close point, then this is 0. So a Cohen-Macaulay module has exactly this property, and in fact, it's characterized by this property. And so I'm saying the same thing is satisfied over here. And so that's really what the Hochster-Hunicke theorem is saying. So now I've formulated in terms of something that doesn't really talk about the Frobenius or anything. I'm just saying you take any variety, you look at the inverse limit of all finite covers of the variety, and this inverse limit object, which might look scary a priori, actually has some really nice structure. It has this Cohen-Macaulayness property, which you can't see at the individual finite levels. It's only visible when you pass to the inverse limit. And so this is the form in which the theorem will become useful in mixed characteristic. And so I wanted to mention it. Okay, and so let me go back to what I was actually doing. So what was I doing? Let's go back. I have to scroll all the way up here. Right, so I was trying to sketch a proof of this theorem in characteristic P. I explained how to kill the cohomology of positive powers of L. We just said you could take power of Frobenius. For negative powers of L, I also sketched an argument, and the idea was you use this Hochster-Hunicke finite cover, which sort of tends to make things Cohen-Macaulay, and then you use a power of the Frobenius. And so finally, it remains to explain what happens with the structure sheaf. And strictly speaking, this is not necessary if you're only interested in understanding the analog of Kodaira vanishing, because I already did that. But for example, if you want to extend the argument I just sketched to the semi-ample and big case from the ample case, you more or less need to know the statement in part C. You need to understand the behavior of the cohomology of the structure sheaf along finite covers. And so I want to do that, and that'll give me another opportunity to advertise the use of X plus. And so that's one reason I want to do this. So let me assume for simplicity now that K is K bar. I mean, I can do that anyways because I'm allowed to go up along finite covers. And so what I'm trying to do is I'm trying to understand the cohomology of X with coefficients in OX and how it varies as X is replaced by a finite cover of X. Now, there are certain finite covers we already know about, which is powers of the Frobenius. And we know that those might kill certain classes in these groups. So for example, if X was a supersingular elliptic curve, then the H1 is one-dimensional, and that H1 is killed by the Frobenius. But if X was an ordinary elliptic curve, the H1 is still one-dimensional, but now it's no longer killed by the Frobenius. So you need to do something else. And so we need to break apart this group into contributions that are annihilated by the Frobenius and sort of the rest. And there's a standard way to do this. So I'll say it this way. It's a standard P-linear algebra. Gives you a decomposition, which is kind of a very kind of poor man version of the Hodge decomposition, if you like. So there's a part on which Frobenius acts nilpotently. It's literally the subspace on which Frobenius is acting nilpotently. And then there's a part on which Frobenius is acting semi-simply. And so what this means is that this is actually generated by Frobenius fixed vectors. So this is the part that needs an argument. So it's always generated by elements, generated as a K vector space by elements alpha with the property that f of alpha is alpha. It's not just a non-zero number. And so this is kind of a standard fact about vector spaces in characteristic P equipped with the Frobenius operator. They're all finite dimensional vector spaces. They always decompose like this. And now this guy over here. So first of all, this part we know how to kill. I mean, we just use a high enough power of Frobenius and that annihilates these classes, because by definition, these are classes that are annihilated by high power of Frobenius. So this part is fine, we can ignore it. And we need to understand how to annihilate these classes by passing to finite covers. And so for that, I'm going to use topology. So I'm going to use the étale topology. And so more precisely, I'm going to use the Arden-Schreier sequence. So the Arden-Schreier sequence will tell me that actually these classes have a very simple description in terms of étale cohomology. They're just cohomology classes coming from the constant sheaf, FP, scalar extended to K. So there's always a natural map from the left to the right, basically because the constant sheaf maps to the structure sheaf. FP maps to functions on X, because functions on X are a characteristic P ring. And the statement is that that map induces this isomorphism, and that needs a small argument. I'm not giving you the argument. But what this is telling me is that if I want to annihilate these classes, it's enough to annihilate these classes. And so now I've translated my problem from coherent cohomology to a problem in topology. So this is kind of similar in characteristic P to what happened in the Kodaira vanishing proof in characteristic 0, where we went from something about cohomology of the ample bundle to something about the topology of the variety itself. And so now the topology is the étale topology, but at least philosophically, the argument is similar. And so what we want to prove is that these groups over here can be killed if you replace X with finite covers of X. And again, you can reformulate the statement as something about X plus this absolute integral closure. And there the statement would simply be that X plus has no étale cohomology, because the cohomology of X plus is the direct limit of the cohomology of all finite covers. If you're trying to prove that the cohomology of any finite cover is killed by a larger finite cover, that's literally the statement that in the limit you have no cohomology. And so therefore the theorem, part C, which we're trying to prove, it follows from the following statement. So, and this is kind of the key lemma, and it's really, the proof, I'll prove it for you. It's extremely simple. It's kind of first course in commutative algebra level special, but it actually is very useful, not just in characteristic P, but also in mixed characteristic. So here's the statement. I'll formulate it in general. So say Y is an integral scheme, is an integral normal scheme with algebraically closed fraction field. So the typical example is Y equals X plus, as above. So it's not going to be Noetherian unless you're like X is 0 dimensional or something like this. So it's this kind of huge object, but the lemma says that these huge objects have no étale cohomology. So then for all abelian groups A, the étale cohomology of Y with coefficients in A is 0 for I bigger than 0. So this is kind of the key vanishing that will in particular imply that these guys are going to be 0 when I replace X with finite covers, but also in mixed characteristic, our vanishing will ultimately come down to this kind of statement using a bunch of Hodge theory. Okay, so are there any questions so far about the statement? Again, I emphasize that like, if you're not used to thinking about these infinite type situations, these are really weird schemes, right? They're not Noetherian, they're not varieties over a field or anything. But I think one of the things that we've learned, and one of the things I would like you to take away from this course is that it's fruitful to work at the infinite level rather than at finite levels, because the statements become much cleaner at infinite levels than at finite levels. And so this is one example of such a statement, and the proof is extremely simple, actually. So let me sketch it for you. And so the proof is the following. So first observation, is that y etal is actually y Zariski. And so what I'm saying over here is that any etal cover of y, actually Zariski locally has sections. So there's sort of no interesting etal topology going on. Everything is just happening in the Zariski topological space of y. And the reason is very simple, right? If you have an etal cover of y, you pass to the generic point. Over the generic point, you have a finite separable extension of your fraction field. But your fraction field is algebraically closed, so there's a section there. And then by normality, the section is going to spread out to a section over the whole space. So you just use that kind of simple-minded argument to see that y etal is y Zariski. But what this means is the cohomology that we're talking about is the same whether I compute it in the Zariski side or on the etal side. Well, if the topologies are the same, the cohomologies are the same. But now this guy vanishes in degrees above 0. I think this is even in Hartshorn. It's Grothendieck's theorem, but it's just a simple consequence of the fact that if you have an irreducible topological space, constant sheaves are Flask, so they have no higher cohomology. And so it's extremely simple when formulated like this. And I think it's actually illuminating to try and go back and see how you would prove this statement about x plus, not by thinking of x plus as a scheme on its own right, but rather as this kind of compatible system of finite covers and trying to make arguments at the level of finite covers. It becomes much messier. And for me, certainly, it took like 8 or 9 years before I went from that kind of messy argument to understanding that this kind of clean infinite level statement is much easier to work with. And so, okay, because of this, we get that these guys vanish. And so in our case, what that tells us is that this group will vanish if I replace x with x plus. And therefore, any individual class is going to die when I pull back to a finite cover. And so that's the sketch of the argument of this vanishing theorem that I wrote over here. So the analog of Kodaira vanishing in characteristic P, where I allow myself to pass up along finite covers. And basically, my goal for the next talk is to explain how this would look like in mixed characteristic. So the statement will look extremely similar. It can't literally be the same because of some characteristic 0 obstructions. Because like a scheme in mixed characteristic has both a characteristic 0 fiber and a characteristic P fiber. And at the level of characteristic 0 fibers, we said that the statements cannot be true. And so you need to futz around a little bit to find the correct statement. But once you find the correct statement, the arguments will be sort of similar. We use some p-adic Hodge theory now to translate from coherent cohomology to topology. And then eventually you go down to this really simple-minded lemma that showed up at the end. Yeah. Okay, so I actually have a bunch more stuff in my notes, but I think that's like a new section and wouldn't necessarily make sense to start now. So maybe it's best if I actually stop here for now, and then I'll take it up. I'll do whatever I need to do next time to cover my needed material.
Okay, well, thank you very much for a great lecture. Are there any questions for Bhargav at this point?
Sorry, so Chenyang asked a question in Delini Luzi, is there an assumption P bigger than dim-x? Yes, absolutely. Sorry, I forgot to mention that. Yeah. Right, that was maybe a bigger obstruction than the ones I alluded to.
Okay, well, if there are no further questions, then let's thank Bhargav again. And I hope to see all of you back tomorrow. Thank you very much.
Mm-hmm.